This was the section that we completed in the last class, I think. Yeah. So we move on to inner product space. The definition of an inner product is clearly a real or complex vector space together with the specified inner product. Okay. A finite dimensional real inner product space is often called a Euclidean space. A complex inner product space is often called a unitary space. Next theorem. Let V be an inner product. Basically, they are defining a norm. Okay. So, norm, do you remember the property of the norm? I mean, this is nothing but this. So, they are about to prove this inequality. I mean, first this, that the absolute value of scalar comes out, then this, then Cauchy Schwarz, and then triangle inequality. Okay. So we can skip this proof, I think, because these are well-known results. This is one very important example. Example 7. Oh, again, I mean, just nothing, just a particular version of Cauchy Schwarz. Which you have already shown. I mean, they are just applying Cauchy Schwarz. Now, once you have defined inner product, the natural, what should the natural thing? What's the point of defining an inner product? I told you, we can define angles, right? Once we have inner product, I mean, what is, we know that A inner product B, I mean the dot product in real maybe, so that is nothing but cos theta, right? So we can define theta like this to be cos inverse So the point is to define sort of right angles or maybe two vectors when we can say that they are standing normally to each other or perpendicular to each other. So you know the definition, alpha is orthogonal to beta if the inner product is 0. And orthonormal if this is 0 with normal alpha, normal beta equals to 1. Okay. These are some examples, you can figure it out yourself. These are not much. These are not very hard examples. Okay. So look at this example 10 carefully. And let's go back to example 3. Just a minute. Where was example 3? Example 3, example 3, example 3. Okay. So this is trace AB star, right? That's the inner product, right? So they are defining an inner product in Mn C maybe, which is A inner product B is trace of AB star. B star is, hope you remember, this is B bar conjugate. So with respect to the this inner product, they are having a look at the basis. I mean EPQ, the basis. 1 at the PQth entry and 0 everywhere else. Okay. I request you guys to just look at these two examples. I'm right here. Just look at these two examples. Example 11, I mean 10 and 11. Just look at it. These are very important examples. Okay. So okay. So see, these are very important. Okay. These are, I think, called those. I mean, Fourier coefficients. Huh? So under the complex inner product of this space continuous real valued functions, this is, I mean, this is a linearly independent set, infinite orthonormal set. Okay. In this way, we get new orthonormal set S, which consists of the functions this. So if these are, see, these are also orthonormal set, huh? But they are making a new one by this. So we will slowly see the techniques to obtain an orthonormal basis from an arbitrary basis. An orthonormal set of non-zero vectors is linearly independent. Okay. An orthogonal set of linearly independent orthogonal set of non-zero vectors is linearly independent. And the technique is very easy. You take an orthonormal set, you take a linear combination, and the inner product looks like this. If V is this, the inner product looks like this. What you have to do is just choose. I mean, you just have to choose this actually. So, suppose alpha 1 to alpha n be a set of orthogonal vectors. You choose Cn alpha n. This is a linear combination. Now, what will you do? Just inner product this with alpha 1. So, this is 0. So, you just do this. So, what will be this? Summation Ci alpha 1 inner product alpha I 0, I running from 1 to n. But this is a linearly orthogonal, I mean, this is an orthogonal set, right? So, if I not equal to 1, for I not equals to 1, this term will be 0. And for I equal to 1, only that term will survive, right? So, you will get this term. This is 0. This means C1 is 0 because norm of alpha 1 is non-zero. And this way you can show that every alpha, every Ci is 0. Okay, so we have to show another thing. This is also very important. So, suppose alpha 1 to alpha n is an orthogonal basis. Okay. Suppose beta is any vector written in this orthonormal basis. Okay. Now, see what we are going to do. Just inner product alpha 1 with beta, and let's see what you get. What is this? Again, summation Ci alpha 1 inner product alpha I. This is an orthogonal basis, so only I equal to 1 term will survive. Thus you get C1 norm alpha 1 square, right? So you get C1 is basically alpha 1 inner product beta by norm alpha 1 square. So similarly, Ci is nothing but alpha I inner product beta by norm alpha I square. So you realize that each coefficient of this expansion of beta, they can be written with respect to this inner product. So beta becomes nothing but summation I running from 1 to n alpha I inner product beta by norm. Oops, I did a mistake here. Ci will be bar. So you do sort of uh, okay. So this is bar is 0, this is 0, and by that we mean C1. If the bar is 0, then C1, I mean this is also 0, right? Or maybe our C1 bar is 0. Okay, so you can categorize all the coefficients of the expansion of beta with respect to that basis. Okay, that was already. Okay, just look at this theorem, look at the statement. Okay, don't see anything else, just look at the statement. This is called Gram-Schmidt orthogonalization process. We are not going to the details. I will tell you the idea. Okay, just look at the statement, please. You have 1 minute, look at the statement. हमेशा एक बार फोन করে দেখো তো পৌঁছেছে খেয়ে দিয়েছি কিনা। So see, I am giving you an idea. Okay. So they are trying to construct an orthonormal basis. Okay. So pictorially, suppose you have been given a basis like this. Okay. Suppose this is V1, this is V2. Okay. These may not be orthonormal. So the first thing they will do is take U1 equals to V1 by norm V1. Okay. That is, you take the orthonormal vector. I mean you take the unit vector in this. Suppose this is one length. Suppose this is of length 1. So this is U1. In the same direction of V1, just this. And then what they do is just draw this perpendicular line and name it as U2. Okay. I mean, this is the orthonormal vector in this direction is then regarded as U2. That is the idea. Now suppose there is another plane. Okay. Now along that plane they will probably choose another orthonormal vector. Now that is how they do it.
We won't go into the details of the machinery because it is not needed. Yeah, you see, that's what they get. This, then again this, then again this, and so on.
The idea is that every finite dimensional orthonormal basis, when you product basis, yeah, you choose a basis, then by ground with orthonormalization you obtain an orthonormal basis.
One of the main advantages with this orthonormal basis is
yes. So see, you look at this. If this is an orthonormal vector, if these are orthonormal, then norm alpha becomes just 1. So you can get rid of this factor. Okay. Like say 1001. Under the usual inner product, this is an orthonormal basis. Don't this grounds me, they will never ask you for this, so you can just keep it. Yes, that was the thing. Suppose W is a subspace of an inner product space V, and let beta be an arbitrary vector in V. The problem is to find the best possible approximation of to beta by the vectors of W. Okay. So what they are doing is basically they are trying to approximate W, approximate beta with the vectors in W. So clearly, if beta is in W, then beta is the best approximation of itself. but actually by based approximation, in a way intuitively they mean beta, the projection of beta onto W. Okay. Yeah. By this we mean we want to find a vector alpha for which beta minus alpha is as small as possible, subject to the constant that alpha should belong to W. Okay. So a base approximation by beta by vectors in W should satisfy this. That is the definition. That if alpha is the base approximation of beta with respect to W, then non beta minus alpha is less than or equals to non beta minus gamma for any gamma in W. Okay. So intuitively they are looking for a projection. Yes, that is. Which brings us to the next theorem. So the statement is like W subspace of inner product is beta, beta is any vector. The vector alpha in W is a base approximation of beta by vectors in W if beta minus alpha is orthogonal to every vector in W. If a base approximation to beta by vectors in W exists, it is unique. And if W is a finite dimensional and if alpha 1 to alpha n is an orthonormal basis for W, then the vector is this. Okay. Clear? Okay. Just look at the statement once again. প্রতিদিন পেটে ঠান্ডা, আজকে গরম দেখাচ্ছে, ঠিক আছে ঠিক আছে, ও পড়ুন, ঠিক আছে সবাই ঠিক আছে। আমাদের নতুন ব্যাচ শুরু হবে ফেব্রুয়ারি এন্ড থেকে, নতুন করে আবার যে টপিক লাগবে আমরা আবার বসে সব ঠিক আছে। এবার নতুন প্রফেসরও ঢুকছে, ঠিক আছে ঠিক আছে। আইএসআই নতুন প্রফেসর, মানে আইএসআই প্রফেসর না, সেখানকার পাস আউট অ্যালুমনাই, অ্যালুমনাই, হ্যাঁ ঠিক আছে ঠিক আছে, একদম সকালে না হোক সন্ধ্যাবেলা যখন, ভালো থাকবে। Hello. Okay. So let's move to the proof. See what they are doing. So first note that if gamma is any vector in V, then beta minus gamma is this. Okay. So they are breaking up this beta minus gamma in this way. That norm of this is basically this. Okay. Using the inner product formula. Now because beta minus alpha is orthogonal to every vector in W, so first they are assuming that beta minus alpha is every orthogonal to every vector in W. Okay. So this vector vanishes. So they get this, which is strictly greater than this. So you have the first inequality. And conversely, suppose this happens for every gamma in alpha, then from the first equation of above it follows that this is greater than equals to 0. So twice real part of this alpha minus gamma 0, because because this is greater than this. In this equation they have just done this, just taken this to this side. Okay. And this is greater than equals to 0 by the definition of best approximation. So that you get this. For all this is true for all W in for all gamma in W. Since every vector in W may be expressed in the form alpha minus gamma with gamma in W. Now see, alpha is in W, right? So every vector in W can be written in terms of this alpha minus gamma. Suppose W belongs to W. So you can just write like W equals to alpha minus gamma, right? So this is gamma is arbitrary. So you can write alpha minus right? So this is our gamma. Thus you realize this statement. Okay, you have this statement. In particular, if gamma is in W, you have, they have chosen a particular gamma, okay, and not gamma, this is tau. For this particular tau, this inequality reduces to this statement. Okay. Now this holds true if and only if this is 0. Okay. Therefore, beta minus alpha is orthogonal to every vector in W. Now once you have this orthogonality condition, suppose there are two approximation of beta. One is say alpha 1, another is say alpha 2. Okay. Then you will realize that this cannot happen. Then you will probably get this, right? But this orthogonality condition will say that so this is one equation you will have if beta has two vectors, two orthogonal two best approximations, and also you will have beta minus alpha 1 inner product alpha 2 is 0, right? Is equal to beta minus alpha 2 inner product alpha 1. These two are 0. Okay. So by this you get so expanding this you get norm beta square plus norm alpha 1 square plus beta alpha 1 plus alpha 1 beta, that is equal to norm beta square plus norm alpha 2 square plus beta alpha 2 inner plus alpha 2 beta. Now, okay, this is your equation, and you can just cancel out these two. So you have this. Okay. Now by this you get beta alpha 2, of course, minus alpha 1 alpha 2 beta alpha 1 minus alpha 2 alpha 1. Okay. Just a minute. They are saying that so they are saying that the base beta minus. How are they proving the uniqueness? Is it obvious? Wait a minute. This is orthogonal to every vector in W. At most one vector. The orthogonality condition is satisfied by at most one vector. Why? Yeah, it will happen, but how it is so obvious? Okay, so I will give you, see, I will have to proceed. So I am giving you a small homework. Okay, use these three expressions. One is this. One is this. Two is this. Okay. Three is this. The next is this. Beta minus alpha I inner product alpha 1 minus alpha 2 is also 0. Okay. For I want to use this to show alpha 1 equals to alpha 2. Okay. That is alpha 1 minus alpha 2 norm is 0. Okay. So try to show this. By these three equations you can show that. Huh? I'm in a hurry to complete this section today.
Now for this, they are taking S is any set. Observe, S is any set. They are defining an orthogonal complement of any set. I request you guys to read this. I mean till this. Please read this.
মা আমার রুমালগুলো কাচতে হবে। বলে দেবো, এখন ফোন করবো। আরে ঘ্যান ঘ্যান করলে ভালো লাগে না। Okay.
So this best approximation alpha is called the orthogonal projection of beta on W.
Then if every vector V has an orthogonal projection on W, then the mapping that assigns each vector V its orthogonal projection on W is we call that the orthogonal projection of V on W. I mean that is from V to W, a linear map sending small v to the best approximation app of V on W. Okay, that's the mapping. And we have seen that this mapping is already defined because there is only one unique. I mean, there is a unique best approximation. So, if V is an inner product space, W is a finite dimensional vector subspace. If the orthogonal projection of V onto W, then the mapping beta from beta to E beta. See, beta to E beta is from V to W. Okay, but they are defining a map from beta to beta minus E beta. This is from V to W part. Okay. because beta inner product beta minus e beta, sorry, this will be 0, I think. I mean e beta, this is in W, and beta minus e beta, this will be 0. Okay. This minus beta minus e beta is W. Basically these two are same, huh? So it will be 0 just. Beta minus e beta is in W part. For any gamma is beta W part, beta minus gamma. They have written it this way, since e beta is in W, beta minus e beta minus gamma is in W part, follows that. So we move on to theorem 5. Let's see. BCS inequality and all that. Theorem 5 is this V is W direction from W part. See, we have already seen that, right? Because you are writing beta as E beta plus beta minus E beta, right? This thing is in W and this thing is in W part. Okay, so this is already proved actually by our discussion. And what is beta minus E beta? This is nothing but I minus E of beta. Okay. So if E is an orthogonal projection of, see, this corollary is very important. If E is an orthogonal projection of V to W, then I minus E is an orthogonal projection of V to W part. This is known as Bessel's inequality. Equality holds if and only I do believe this statement is enough. Don't need too much stuff. I mean, not the proofs. These proofs are, I mean, not very difficult. Find a basis. the distance between two vectors. This is standard now. By norm, they are defining a metric. Okay. You have inner product, alpha inner product beta. C. So by that you define a norm of alpha. That is this. Now you are defining d alpha beta, that is distance between alpha and beta, by norm this. So from an inner product you define alpha, from alpha you define norm, from norm you define metric. But I am giving you a question. I mean, this is this direction, right? From this to this, from this to this, right? But can you go reverse? I mean, if suppose I give you a metric, can you give me a norm? Given any metric, is there a norm such that which will induce that metric? Well, that's not possible, because if you see, I mean, suppose I give you, for an example, suppose one thing you should observe, right? Like d alpha beta, right? What is that? That is norm alpha minus beta, right? What is this? Distance from, I mean, rather distance between 0 and alpha minus beta, right? But the issue is an arbitrary topological space may not have 0 in it, right? There may not be a 0, I mean, there may not be an additive identity. So if there is an additive identity, you can probably define, suppose you are given a metric, okay, and I want you to see it as a norm. So you probably can write dVW as norm v minus w. But the problem is that, I mean, I want to define like this, right? That d alpha beta, I want to define this like distance between 0 and alpha minus beta. But the problem is there may not be any 0. Okay. So not every metric is induced by a norm. Now the opposite. Is every norm induced by a metric? Is every norm induced by some inner product? That's not true either. A norm is induced by an inner product if and only if it follows the parallelogram law. Remember this statement very carefully. A norm is induced by an inner product if and only if it follows the parallelogram law. Okay? So like this norm, suppose norm fx, where in on C01, okay, you define it as sup norm fx, x belongs to 0, 1. This is not induced from an inner product, okay. You take like the norm p, which will be like this, norm, I mean, mod fx to the power p whole to the power 1 by p 0 to 1. These are not, this is induced by an inner product if and only if p is 2. All of these are provable, and you will probably see few of them once you learn functional analysis. But this is an inner, but I mean, okay. B is an inner product, so that alpha is equal to, okay. Can you do this? Can you do 5? Okay, you have 2 minutes, try 5.
Okay. So see, this is clear, na? If alpha equals to beta, then of course, I mean, alpha minus beta is basically 0. So 0 inner product gamma, this is alpha inner product alpha beta, this is 0, and this implies alpha inner product gamma. So this part is very easy. For the other part, can you do the exact opposite thing? Like, suppose alpha inner product gamma is beta inner product gamma, okay, which implies alpha inner product beta. This is to be 0, right? But can you conclude for every vector gamma belongs to V? So can you conclude that alpha minus beta is 0? If a vector, so if V inner product gamma is 0 for all gamma belongs to V, can we say V is 0? The answer is yes. How? See, this equation is true for all gamma, so you can choose gamma equals to V. Okay. Now you get V inner product V. This is 0, which implies norm V is 0. Now norm V is 0 if and only V is 0. No? Okay. So this implies alpha minus beta is 0, which is alpha equals to beta. Let W be the subspace of R2 spanned by vector C, 4 using the standard inner product. Let it be the orthogonal projection of R2 onto W. Find a formula for E x1 x2, the matrix of E in the standard basis, W part, an orthogonal basis in V is represented by the. Okay, so 6 is very important. Okay,
So we will do 6. First read the question and tell me if you understand it or not. So first let us define a formula for E x1 x2. Okay. So as far as I recall, there was a formula given here, right? What was that? There was a formula for alpha given. Where did it go? Yes, that is right. If alpha is the best approximation of beta, so this is how it looks like, right? So we will apply this. Okay. So E x1 x2. So what will it look like? Just remember this formula. So you write x1 inner product 3 comma 4 by norm 3 comma 4 square into 3 comma 4, right? By that formula. So you know how it looks like. This is the dot product. So just this. So this is the formula for ex1 comma x2. Okay. The matrix of E in the standard order basis, I think you can do it yourself. Please do it yourself. Okay.
Okay, I mean, let's do it anyway. E10 is just by putting it, you get 9 by 25, comma 10 by 25, and E01 is just 12 by 25. Okay. So C, yeah, and then the matrix is given. So W part has dimension of course 1 because W has dimension 1. And we saw that this is the this was the thing, like Ex1 comma x2 belongs to W part for all x1 and x2, right? Now see, so it is enough to find one non-zero vector in W part, right? Because W part is spanned by dimension W part is 1. Okay. So it is enough to find one non-zero vector. So you just put x1 x2 equals to 1 comma 0. Okay.
So 1 comma 0 minus E1 comma 0 was this. Okay. So call it alpha. So W part is just spanned by alpha. Okay. So it is nothing but 4 comma 3. Okay. And if you write D, an orthonormal basis, just normalize it. That is just divided by the norm. Okay. That's it. Okay, we will stop today's class here and we will start from this exercise in the next class. Try it.